Okay, so thanks for coming. Thanks for allowing me to give the talk. I know we set this up without a lot of notice, so I appreciate both the effort to set it up and all of you making your time to come. I'm excited to be here. I hope you enjoy the material. Some of the things that we want to do in the future on Mars are things in robotic mobility, ground vehicles or air vehicles that I know you do related research on here. And I was hoping to find some ideas, some potential collaborations. We visited Panavision this morning, had a very good meeting, got some good ideas, and found one exciting possibility to collaborate on. So it's already been very valuable for me. Just quickly to outline what I'm going to talk on, I'm going to give a little bit of background on Mars and why we explore there. I'll talk about recent achievements with the Perseverance rover and the Ingenuity helicopter. I'll give you a quick overview of the next thing that we're working toward, which is bringing samples back from Mars. And as part of that, we're working on an upgrade to the Ingenuity helicopters to be a backup method to retrieve samples. And then I'm going to talk about future prospects, where the main things I'll discuss are there's a vision for a very long-range rover for the moon that would drive up to 2,000 kilometers in 3 or 4 Earth years, which is a factor of more than 10, more than we've ever driven on another target body in a factor of 5 less time. So almost 2 orders of magnitude more distance per time. And if time permits, I'll talk a little bit at the end about broader future objectives. So just quickly about Mars, about half the diameter of Earth. It's about 1.5 times as far from the sun as the Earth. So we can use solar power, but we don't have as much of it. Gravity is about 1/3 of Earth's. It's quite a bit colder, so can be as warm as plus 27 C at noon on the equator. But where the Perseverance rover is, it gets down to about minus 80 C at night. At the poles, down to about minus 128 C. For aerial mobility on Mars, an important fact is that the density of the atmosphere at the surface is only about 1/100th of the density at the surface on Earth. And then a useful fact for knowing about Mars operations that the length of a Mars day is about the same of an Earth day. We call a Mars day a sol. If I use the word day and sol interchangeably, that's what it means. Now, why do we go there? So for decades, there have basically been these 4 themes for Mars exploration. Try to understand whether there was ever life or currently is life, or was any chemical evolution in organic molecules toward life. Understand the climate history of Mars, understand the geological history of Mars. And these are all things interesting intrinsically for Mars, but if we learn about them there, they'll teach us about planets in more generally. And then through the history of Mars exploration with robots, we're learning things that we think will help us eventually send a human mission. And it's a strong goal of NASA right now to get first humans back to the moon, and then beyond that to Mars, hopefully in about 20 years. And one of my goals is to try to enable use of mobility systems, robotic mobility systems, as part of future Mars, a human exploration of Mars. So we'll see how that goes. All of these things are linked by the fact that water plays an important role in them. We know from orbital observation that there's been a lot of that there has been and is currently still a lot of water on Mars. So there's water in the north and south polar caps. We can see ancient river channels that are as much as 3.7 billion years old and more recent. And so we've had missions that landed and proved conclusively that there's water hydrated in the minerals and buried in the shallow subsurface at high latitudes. So then the exploration themes transition from just go and understand the history of water to, well, there was water, but is it really habitable? And that requires a certain set of elements as building blocks. It requires chemical disequilibria to provide the energy for life. It's most probable if that water had a neutral pH instead of being highly acidic or highly basic. So after that, we had the Curiosity rover mission that was exploring habitability. It proved that there were habitable environments on Mars. Now we're seeking signs of past life or chemical evolution toward life with the Perseverance rover. And that requires scientific instruments that we can't do it all on the surface of Mars. We have to bring samples back. So the main goal for the Perseverance rover is to collect samples, leave them on the ground on Mars, and then we'll send another mission in a few years to go and pick them up. That's a collaboration with Europe. And all of this, again, is preparing for human exploration. I'm not going to spend much time on this slide for lack of time, but just shows the history of missions in the last 20 years and a couple of things that we hope to fly in the next few years, and also international missions. They're shown in orange. So just to highlight a few things, you see the Curiosity rover over there kind of on the left. It's still operating. It landed in Gale Crater, which is about 150 kilometers wide. It has a mountain in the middle that's about 5 kilometers tall. And we know that that mountain was built up in layers over time. And so the lowest levels of that mountain are the most ancient. And as you go upslope, you get into more recent terrain. And so by going upslope, we're hoping to learn about the history of the climate on Mars. And so at the bottom, we found a place where we know the water was neutral pH, had the right elements, showed evidence of chemical disequilibria, showed evidence of long-term water bodies. So that's where we convinced ourselves that there really were habitable times and places on Mars. And as we go upslope, we're going into layers where there are more sulfate minerals, and that's evidence of climate change on Mars. So we're hoping to understand more about why did the climate of Mars go from being somewhat habitable to being so uninhabitable today. I'm going to just skip over the rest of that in the interest of time. This is a family photo of the rovers that we've sent, the smallest one at the bottom being Sojourner. These are launch dates. That one launched in 1996. Over on the left is a model of Spirit and Opportunity. On the right is a model of Curiosity, and then Perseverance is almost a carbon copy of Curiosity, but with different instruments. And for the purpose of today, one of the important things that's changed here is the amount of computing power on board. So Sojourner only had an 8-bit microprocessor with about a 2 megahertz clock. From there, we went up to about 20 megahertz with an early PowerPC architecture. Curiosity had a PowerPC 750, but the clock rate was still only about 132 megahertz. So finally, with Perseverance, we added a coprocessor with a field programmable gate array. That let us do some of the onboard computer vision in real time. So stereo vision, so we do 3D perception with 2 cameras, and visual odometry. We track features on the terrain with those cameras to estimate the motion of the rover. We can now do those in a fraction of a second per frame on the FPGA, and that lets us transition from taking maybe a minute per meter in fully autonomous mode to where we can drive continuously at the peak mechanical speed of the rover, which is still only about 4 centimeters a second. But it's made a big difference, and I'll talk later about what we hope will be the next revolution in onboard computing for planetary exploration. So things that are new in this mission that we call the 2020 Mars mission, we've got a new set of scientific instruments to support this objective of searching for signs of ancient microbes. To support the sample return objective, we have mechanisms for sample acquisition, caching samples within the rover, and then later on drop them on the ground. I'll talk about that a little bit more. We picked a landing site in a crater where we could see that there had been a river delta. So there had been a long-lived lake. To land there, we had to land far more precisely than ever before. So we developed something we call terrain relative navigation that let us avoid landing hazards that we could map from orbit. We needed to drive a lot faster, so we developed this coprocessor and put the vision algorithms in there. We needed to be able to drive over rocks that were low enough instead of drive around all the rocks. So we developed a smarter path planning algorithm. And then we developed this little helicopter we call Ingenuity, which is a technology demonstration. It didn't go up there to actually participate in the science, although it is now contributing to scouting for the rover. And so that's been the first ever demonstration of a heavier than air aircraft to fly on another planet. This is an artist's rendition of the Perseverance rover. I'm not going to take the time to talk about all of the scientific instruments here. That arm has a fairly heavy payload out on the end of the arm, including some scientific instruments and a core drill. So it will drill up to about 6 centimeters deep, get rock cores, and then it can fold back into the front of the rover. There's mechanisms in there that will hermetically seal those samples in tubes, like shown here. That's something like 4 to 6 inches long. I don't remember exactly. It saves those in a carousel on board, and we're going to drop 2 caches of samples. So we've already dropped 10 samples, and those are just spaced out over the ground. And then toward the end of the mission, we're going to drop another 20 or 30 samples. And then in maybe 7 years or so, if all goes well, we'll have a lander that lands within about 700 meters of those samples. And I'll talk later about how we get those samples back to the lander and bring them back home. So where did Perseverance go? It landed in Jezero Crater. This is a false color elevation map of Jezero Crater. It's about 45 kilometers in diameter. And there's a little river channel that you can see on the left coming in, and a river channel that exits on the right going out. And I'll show you a little bit better in a second here, but there's a river delta on the left at the inlet channel. And there's a little black ellipse, which is the landing ellipse. So that's the margin of error for where we're going to land. It was about 7.7 kilometers in long axis. So we had a 99% probability of landing somewhere in there. And you can see it overlaps, or you'll see better later, it overlaps the delta. So we had to do even better than this to land safely there. This is an artist's rendition of what that might have looked like 3.5 billion years ago. And here's a close-up of the delta and a little arrow that shows the vantage point of this kind of elevated 3D rendering to illustrate what we're looking at there. And the little red X is where we landed. So what we're hoping to find is organic minerals that would be evidence of some kind of chemistry, showing evidence of life, or at least molecular evolution toward life. And those might have been carried in, if they existed, deposited at the delta, and then preserved in the sediment materials in the delta. So that's really why we targeted this site. One of the important advances here is this precision landing capability. So the little white lines here are parts of ellipses that show the evolution of landing precision since the Mars Exploration Rover mission way back 20 years or so ago, where this landing ellipse was 200 kilometers long. And it was that long mostly because we didn't know enough about the atmosphere. We weren't sure how dense it was, weren't sure how tall it was. We enter the atmosphere at a very shallow angle, so that makes the uncertainty very stretched out in the downrange direction. And then as time went on, we got better models of the atmosphere, and that let us reduce this landing uncertainty for the Phoenix and InSight landers to about 130 kilometers. And then for Curiosity, we added something that we call guided entry. And so the way that landed is at the top, we have entry with the heat shield. When the velocity gets low enough, we deploy a supersonic parachute. Once we get subsonic, we drop the heat shield. And in this case, the rover had basically a propulsive backpack. And so that combination of the rover and the propulsion system dropped out of the back shell, and then it flew to the side by several hundred meters so that the parachute and the back shell wouldn't come down on top of the rover. And then that system came to a hover about 20 meters off the ground, and we lowered the rover down on a cable. And it landed on touchdown, the cable cut, the propulsion system flew away and crashed. So part of this was something we call guided entry that reduced the uncertainty of that ellipse from about 130 kilometers for the Phoenix and InSight landers to about 25 kilometers for Curiosity. And the way that works is before we get to the planet, we kick a few weights out of the back shell, which creates an off-center center of gravity. So when we hit the atmosphere, there's a lift vector. And then there are reaction rockets spread around the back shell that let us roll the spacecraft. And that lets us point the lift vector. And we've got a navigation grade inertial measurement unit in there that we can integrate. So we know where we are at atmospheric entry to within a few kilometers. We can integrate that forward so we know where we are still very accurately. And if it looks like we're either going long or going short, we roll the lift vector to significantly reduce that downrange error. So that was a critical advance in Curiosity, but it wasn't enough for Perseverance because we've got this landing ellipse here and everything that's marked red. So this is 7.7 kilometers long and the delta's on the left. Everything that marks red is too hazardous to land on. So I don't remember the percentages, but a high percentage of this ellipse was too hazardous to land on. But we've got imagery from orbit at 30 centimeters per pixel. From that, we can create elevation maps at 1 meter per pixel. So we can map almost all of the landing hazards from orbit. So then the question is, where are we as we're coming down relative to that map? And can we do trajectory planning on board in real time so that we can use that propulsion system to steer and land precisely and avoid all those landing hazards? So the path planning algorithm exists to do that as long as we know where we are. So doing that is the system we call terrain relative navigation. I was personally involved in the initial creation of this. And so with this, as soon as we drop the heat shield off, now we have a camera that can see the ground. And we take pictures at between 3 and 4 kilometers above the ground. And we find textured parts of those onboard images. And on board, we can match them in real time to maps that we've created from orbital imagery. So we have the orbital image maps and elevation maps. We do this onboard landmark matching that gave us position knowledge to plus or minus about 40 meters, 3 kilometers above the ground. So then we come down further, and when it becomes time at about close to 2 kilometers above the ground, the rover drops out. Now it knows where to go. And we could divert up to about 700 meters and land in a safe place. All of that computing was done with this field programmable gate array coprocessor on board, which is one of the innovations here. I don't think I have time to get more in the details. I put another slide in case there are computer vision people that wanted to know more about it, but I'm going to skip over that. You may have noticed I put a few citations in these slides. I can make these available later if there's interest, and you can go and look up some of the papers if you're interested in knowing more of the details. I'm also going to go a little bit fast for now over things we'd like to do in the future, but this system needed an altimeter, and we had a fairly big and heavy, expensive radar altimeter. We want to be able to operate without that. So we want to be able to do the landmark matching in a way that is invariant to scale. And so we're working on a couple different approaches to do that without knowing altitude in advance. We need to make it more tolerant of wider illumination variation between the orbital imagery that has been acquired at the equivalent of about 3 in the afternoon lighting. The lander might in the future come down much different time of the day. We needed to make more tolerant of lighting changes, more tolerant of uncertainty in the orientation. So right now with that inertial measurement unit, we know our heading very well when this has to operate. In the future, we want to use smaller, cheaper inertial measurement units. So we need vision algorithms that are less sensitive to uncertainty in the orientation. And I'll come back later to what we're doing to have a much more advanced processor. Now I'm going to talk about a little bit about the rover navigation. So there are a lot of cameras on this rover. We don't have space qualified laser rangefinders or LiDARs yet. So we use stereo vision a lot. So that's a pair of cameras that can do depth perception and visual feature tracking. There's a stereo pair on the mast with about a 45-degree field of view that we use for planning paths 10 or 20 meters ahead. And then there's stereo pairs on the front and the back with about 150-degree field of view that we use for planning manipulation activities in the first few meters in front of the vehicle. Things that were challenges in this mission, we needed to be able to drive a lot faster than before, go farther every day. I'm not going to talk too much about that. Things that we don't do on board yet is we don't recognize, I call them drifts. You can think of them as sand dunes. So the picture on the lower right is a picture from orbit. For scale, the line in the middle there is about 50 meters long. So there's these sand dunes everywhere on Mars. We've had rovers get stuck in those and almost kill the mission. So right now, people on the ground see where those are and put in waypoints that make the rovers go around them. Eventually, we want to be able to recognize those on board. We haven't matured the vision algorithms and the computing power to be able to do that on board yet. And right now, the rovers don't have the ability to do landmark recognition. So we can do what we call visual odometry and wheel odometry, so we can integrate measurements to estimate where we are, but that integration has error, so the error grows with distance. To be able to have bounded position error, we need to do something else, and on Mars, there's no GPS, so we need to recognize landmarks. Similar problem to what we did for the landing system, we need to recognize features we see on the ground to things that we can see from orbit. So we're working toward that. This path planning problem I mentioned, we needed to be able to straddle rocks instead of go around all the rocks. That's illustrated by the cartoon on the left. To be able to do that, we slightly generalized a technique that's known in this literature as kinematic settling. We have a model of the geometry and the kinematics of the vehicle that you settle down on an elevation map, and you can check to see if there's enough ground clearance. And we generalize that to be able to account for possible slip. And then since the rover can't steer and drive at the same time, we drive these fixed circular steering arcs for a ways, and then we stop and we change the steering, we drive another steering arc. So that's led to a path planning paradigm that's a tree search, where we're basically searching a tree of circular steering arcs as we go. Computational complexity of that isn't very good. It's exponential with the number of search plies. So if we can do simultaneous steering and driving, we can also have, besides more powerful path planning algorithms, we can have better computation complexity in that respect. We have a route planner that uses elevation maps at this 1 meter per pixel resolution, and it picks up where the local path planner leaves off and gives us a route in a 200 by 200 rover center map. Now the helicopter, this actually got started. There was research in NASA and other places around the country back in 2000 to 2005 on the aerodynamics that showed that it's possible to fly on Mars aerodynamically. But then interest in that kind of waned. I think the funding went away. And then the Army got interested in autonomy for drones. And some of you know that the Army had a project called Micro-Autonomous Systems Technology for 10 years that Penn was a big player in that, did a lot of important work in autonomy for drones. I was fortunate to be part of that project as well and did some autonomy for drones as well. And one day in 2013, the JPL director was going around seeing what was going on at JPL and came to my lab and saw work we were doing on autonomous vision-based landing toward being able to land on rooftops for persistent surveillance. And he asked me, do you think you can do that on Mars? And I said, I think so. And that was the start of building this. He thought that was quite an interesting possibility. Our initial ambition was to build a helicopter that could be a scout for a rover. Turns out we didn't have enough money to realize, at least we didn't think so, that full vision. So we built this as a technology demonstrator to prove that it's possible. The whole thing weighs about 1.8 kilograms. As you can see in the diagram here, the rotor diameter is about 1.2 meters. I'm not going to talk about everything here, but it's solar powered. So there's a rectangular solar array above the rotors that we can recharge in a couple of days. It has a warm electronics box that's insulated, that all of the electronics is inside. For scale, that's about 15 centimeters on a side. The sensors here are a pair of cell phone cameras. There's a black and white one that looks straight down for doing navigation. And there's a color one that looks ahead. We send pictures home for, public outreach and for the scientists to do reconnaissance. It has a very small MEMS inertial measurement unit. It has a Garmin laser rangefinder with a maximum range on Mars of about 14 meters that we use as an altimeter. It has a more accurate inclinerometer we use for initializing attitude before takeoff. And this is the computing architecture. So to be light enough weight and high enough performance and low enough power, we had to use all commercial grade components. None of the standard space qualified hardware. So we do our flight control with microcontrollers from Texas Instruments that are dual redundant. They have 2 processors operating in lockstep, executing the same instruction at the same time. If they disagree, an error flag goes up. We have 2 copies of that. So there's one that's currently controlling the helicopter, and then there's a hot spare. So if the error flag gets set, we switch to the hot spare and it takes over. That doesn't have enough computing power to do the vision-based navigation that we need. So we have an old generation cell phone computer from the Snapdragon product line at Qualcomm. We only had enough mass capability to carry one of those. So there's one Snapdragon 801 that does vision processing and a state estimation filter I'll talk about in a minute. And then all of our sensors and motor controls go through a small space tolerant, space qualified FPGA. So this little MEMS IMU has way more drift than we can tolerate by itself. So it gives us attitude knowledge at very high rate, but it drifts very fast. So if you're in this field, you know about these things. If we track visual features, we can greatly reduce the drift of our velocity estimates and therefore the drift of our position estimates. So we use pretty well-known algorithms, the fast feature detector and Lucas Canati feature tracker in an image pyramid. We pick features in a 3x3 grid over the image. We track them for a while, and then to avoid them all drifting out of the image, we throw them all away and we pick a new set every 10 frames or so. And the way this works, we're assuming that we're flying over pretty flat level ground. We're pretty compute limited, and we are limited in the time and money we had to develop this. So we assume everything's at the same distance. We can measure that distance with the altimeter. We pick our features in a base image, and then as we go, we call the next images search images. So we're matching features from the base image to the search image until we need to pick more. So then we establish a new base image. And so this has worked very well. It's kept us safe. We started out with no ability to detect landing hazards on board. We've since added a very simple landing hazard detector that's based on these features. So wherever there's a lot of features, there might be rocks. Where there's no features, it's probably pretty smooth. We use that as a heuristic to find places that are probably safe to land. In the future, we need something more sophisticated that really perceives the geometry of the terrain to make it safe to land. So Ingenuity got to Mars on the underside of the rover. Rover landed as shown there. The white line up through the middle was about 50 meters long. The original plan was to just do 5 flights. This is a video shot by the rover of our very first flight. It went up 3 meters, hovered for about 30 seconds, and then landed again. So for us, that was a history-making moment, just to show the technical feasibility of this. Now, what we've done here, the white line shows where the rover's gone over the course of 2 years. The green line shows where the helicopter's gone. The helicopter has actually started to do scouting for the rover to make sure that places that the scientists are interested in going with the rover are both safe for the rover to drive and as scientifically interesting as they hope. We've explored the front of the delta. We're now up on top of the delta looking for things there, and eventually we'll exit the crater and go explore even older terrain outside the crater. So I'm going to skip over this. That's kind of a detailed slide on how we plan to do Mars sample return. I can talk about that a little bit here. So we'll have a lander. That lander is going to have an arm. If Perseverance is still operating, it will drive up to the lander and just drop these sample tubes on the ground in front of the lander. That arm will pick up those tubes, put them in a basketball-sized container, and then we have a rocket that launches those up into Mars orbit. Europe is building an orbiter pictured here. It will rendezvous with that sample container in orbit, hermetically seal it in a capsule to return to Earth. Now, if the rover doesn't survive that long, our backup plan is to use helicopters. So they're like Ingenuity, but we're adding wheels. We'll do skid steering. They will land a little bit in front of the sample tubes and then drive up and pick them up. So we need the ability for that to be safe and to know where those are. So we will map that area and then do basically the same kind of landmark recognition for the helicopter that we did for the lander, so we can keep track of where the helicopters are. We're adding stereo cameras to the front of this so we can do 3D perception on the helicopters. Yeah. So what we've been doing so far is before we land, we take a picture when we're 5 or 10 meters off the ground. We send that to Earth. We've got orbital images at 30 centimeters per pixel. On Earth, people can register those. Now we need to by hand. That's what we do now. So what we're going to do in the future is the helicopter will fly out and get mapping imagery. We'll downlink that to Earth. We'll build a map here, and then we'll upload that. And then the helicopter will do the registration on board. So that's how it will know where it is in the future. We'll use those stereo cameras to do visual odometry and obstacle avoidance for the helicopter like we did for the rover. And then those two helicopters will take turns, bringing one sample tube at a time back to the lander. Now, once we've built this, we have the possibility of repurposing it for some future mission. So we're not going to need those wheels all the time. We're not going to need this arm all the time. We can take those back off and put scientific instruments on there. So there's interest in putting magnetometers on and going and mapping the ancient magnetic fields in the crust on Mars. We can put more precise accelerometers on and go and make gravity measurements if we can land at the bottom and the top of fairly large changes in elevation. We can estimate the density of the crust in there. That is useful to understand the history of the geologic evolution of the planet. That's about all we can do with a helicopter that's this small. So to do more science, we need a bigger helicopter. I'll talk about that in a minute. I mentioned at the start that there's interest. I'm going to talk a little bit about the moon and then come back to Mars. So the next big opportunity for rovers is likely to be a rover for the moon. And this concept called Endurance of a rover that will land on the lunar far side in a place called the South Pole Aitken Basin, which is one of the biggest impact basins in the solar system, and therefore very ancient. And the idea is to land in the middle of that and drive about 2,000 kilometers over the course of 3 to 4 Earth years and pick up samples at about a dozen locations. And then go to the region of the South Pole and rendezvous with astronauts that would land there and bring back about 100 kilograms of samples. And when we get them on Earth, we can study the mineralogy and chemical composition in detail and do absolute age dating. It's called geochronology. And if we do that, then we can, what we do call calibrate the crater record. Right now, we estimate the ages of planetary surfaces by counting the craters. And we want to get absolute measurements and compare that to the crater frequency. And by doing that, we can get a better idea of the age of all of the surfaces of rocky bodies in the solar system. So that's scientifically important. It has significant challenges, like I think I was saying earlier, for autonomy. So to do this, we have to be able to drive 10 times faster on average than we have today. We have to do it both day and night. So far, we've only done operation in the day. We have to not have to stop to call home to get human help as often. So we need more reliable onboard autonomy that can detect and recover from faults on board more successfully. We need better position estimation. So we need to know where the rover is. The two obvious ways to do that are either have an orbiter that has a radio frequency navigation aid that helps the rover know where it is, or onboard landmark recognition. So I've been working on that. We can, most of the moon now, I think I mentioned this earlier, is mapped in the sunny parts to a resolution of 50 centimeters per pixel. There's a new camera orbiting the moon on a Korean orbiter that can image the permanently shadowed areas with a resolution of about 1.7 meters per pixel. So with that, we can create maps of crater landmarks from orbit. And then if the rover, so I've got some cartoons here that kind of just illustrate the idea. In the upper left, this is a sketch from Apollo era. If you can drive kind of up to these craters, and then you look at the picture at the bottom, if the rover can recognize these craters and correspond them to the orbital crater map, now we can estimate the rover position. That's going to be probably a pretty noisy, error-prone process. So it really needs reliability. I think it's a tailor-made application for particle filters, but you know, this is an area where we've done some work. I think some valuable proofs of concept, but there's a lot more work to do to make this a really reliable capability. I just threw in one illustration of some results. This is a stereo pair from one of the Chinese rovers on the moon. Fairly narrow field of view of about 18 degrees. And there's a crater in the middle there. It's a little hard to recognize. This is a stereo disparity map. So basically grayscale codes distance. The brighter it is, the closer, the darker, the further. And you can see the outline of the crater in the middle there, where there's white means there's no data. And then this is a rendering, kind of a 3D rendering. The yellow dots mark where we've detected the leading edge and the far edge of the crater. Where there's holes, there's either the terrain is self-occluded, we can't see in the near side of the crater, or there's part that's occluded on the far side of the crater. And then we basically fit an ellipse to estimate the center of the crater and its diameter. And right now we're treating this as a geometric problem to match that stuff to the orbital map. So I'd welcome interest in working on this problem to help us solve this problem better. I'm getting close to the end here. So where are we going in the future? There are a number of studies that have been done to, let me back up. So NASA has been working toward this sample return objective for decades. It's very expensive. We're kind of coming to the point where we hope we're going to achieve that in the next 10 years. So now we need to kind of refresh our goals. So there have been several studies over the last 3 years or so to lay out a new set of scientific goals and a new technical approach for the next 20 years of Mars exploration. So I won't take too much time to go into the details here, but we've got new science objectives to study the ancient climate, ancient habitability. If there ever was life on Mars, or might still be life on Mars, the most likely place that it was underground, like in groundwater on Earth. So we'd like to start exploring the subsurface, get deeper underground. There's a lot of ice at the poles and underground in the high latitudes. That's evidence of more recent climate change. We'd like to study that. And then just in general, understand Mars used to have an atmosphere about as dense as ours. Where did it all go and why? And then I mentioned that there's ambitions to get people to Mars. You know, the time frame is uncertain, but currently hoping for some time in the 2040s. Potentially, robotic mobility systems could be a good augmentation of that, and I'm hoping that we make this possible. Just 2 days ago, the director of the Mars exploration program at NASA headquarters gave a public talk about the draft strategy that we're formulating. It's now available on the web. I'm not going to talk about that here, but you can look it up, and I've got time afterwards. I'd be happy to talk more about it if there's interest. This is an illustration of one of the things that we're working on to try to make it cheaper to land on Mars. This is a hard lander, so it doesn't use a propulsion system to do a soft touchdown like all of our landers to date. It comes in with a heat shield, and when it gets subsonic, it deploys a drag skirt that's cloth to increase the drag area to slow down the velocity, and then it has a steel impact attenuator, and it just does a hard smackdown at 1,000 or 2,000 Gs. That impact attenuator compresses. We think that it's quite possible to have electronics that will survive that impact. So with this approach, we think we can deliver about 10 kilograms of science instruments, which is enough to do enough types of science to make this worthwhile. And we believe this could be a lot cheaper than what's been done to date with propulsion systems. We really want to be able to do more science with helicopters. That requires bigger helicopters. So we'd like to be able to carry, it's a typo here, it's not 5 kilometers, it's 5 kilograms of science payload. To carry 5 kilograms of science payload requires a much bigger helicopter. Our current estimates are that that would be 40 to 50 kilograms total. The rotors are the individual rotors are the same diameter as Ingenuity, but with a hexcopter, the whole thing would be about 4 meters tip to tip. So, you know, this is in early development, so a lot of this is still highly uncertain, but we're aiming for cruise speeds up to about 30 meters per second. And by the way, we don't do this ourselves. We have collaborators at NASA Ames and AeroVironment and elsewhere. We need to give everybody credit. We're not really sure how far we're going to be able to fly yet because there's still a lot of uncertainty in the mass, and it depends a lot on what altitude or elevation we're flying at. But we're hoping for 5 kilometers or more per flight, which is about 10 times more than Ingenuity does per flight. And the kinds of science instruments could include imaging spectrometers that tell us about minerals, other instruments that tell us about the specific chemical content, which is important to know, and even a small ground penetrating radar with a resolution of about 10 centimeters vertically and a depth penetration of more than 20 meters. If we went that to the North Pole, we could study layering of ice at the North Pole, which would teach us about climate variation in perhaps the last million years. There are a lot of challenges to make this possible. So right now, Ingenuity communicates through the rover at a maximum distance of maybe 0.5 kilometer. So we need to be able to communicate from the helicopter directly to orbit. That takes a much different radio. To make that light enough is a big challenge. It needs more autonomous navigation capability, so it needs to generalize that visual inertial state estimation algorithm to be able to fly over arbitrary terrain. It needs 3D perception of the terrain for safe landing. It needs global position estimation, so we can do that landmark matching to the orbital maps on board. And what I was talking up at Pennovation with today with the students there was we'd like to be able to do onboard wind estimation in flight. That would help us a lot. So that's an interesting idea to collaborate on. And then we need more onboard computation power, and we need a way to land affordably. And so to land affordably, if we put it on one of those propulsive landers and had the propulsive lander go all the way to ground, we're not going to be able to afford that in the mission class we'd like to be in. So we're studying mid-air deployment of helicopters on Mars. So on the left would be what we're calling rotor only, where the helicopter is in this structure we call the back shell, and at some elevation, maybe 1 kilometer above the ground, it drops out, spins up the rotors, gets under controlled flight, and goes to land. So if you've heard about the Dragonfly mission to Titan, Saturn's moon Titan, that's the way it's going to land. That's harder on Mars in the thin atmosphere and the higher gravity. So we're probably not going to do that. Over on the right is the idea that if we add a secondary parachute, that could slow us down more. That makes it a little bit easier. We're probably still not going to do that. The idea in the middle is something we're calling a jetpack, where we have a hydrazine-powered propulsion system, and the helicopter is all folded up. It sits on top. And then that drops out, and the propulsion system carries us away from the descent system and comes to a hover about 200 meters off the ground in around 0 airspeed. And then we can deploy the rotors, spin up, take off, and then go land safely. So that's what we're working toward. That looks like it's possible. Right now, we're working on the propulsion and control. We still need state estimation and the landing hazard detection I was talking about earlier for this as well. Higher performance onboard computing. So the ability to use this cell phone class processor on Ingenuity, nobody ever did that in a planetary mission before. So that was revolutionary. And the automotive industry needs levels of reliability that are in family with what we want in planetary missions for human safety, for self-driving cars. And so companies like Qualcomm are working hard to make their processors have the levels of reliability that we need, including those dual redundant lockstep microprocessors, including other redundant computing resources on the chip. So we've been working closely with Qualcomm to try to enable using basically much more recent generations of Snapdragons in the future. We have prototypes of those. On the left, you see a board that's 69 by 94 millimeters, and there's a bit of a sketch of the computing architecture there. So it's got ARM CPUs, up to 8 of those. It's got digital signal processing elements. It's got a GPU. Basically, a lot of horsepower in a very small, high-performance package. It's got a deep learning accelerator. This would further revolutionize what we could do for any mobility system, including rovers. Now, that's not the only game in town. This would never be fully rad hard. We're always going to have bit flips. So NASA's also putting a lot of money into something called high-performance space computing, which would be more inherently radiation tolerant. We could go to higher radiation environments like Jupiter with something like that. But that's still further in the future. The Snapdragon stuff is here today. We're trying to make it possible to use that and then ride the curve of industry advancement in that. So last slide. This is a sketch, just purely conceptual. Take it with a grain of salt. But what a human landing campaign might look like. I call it a campaign because it would be more than one mission. So you would have perhaps a couple of cargo landers, one on the left that would bring extra fuel. It might bring robotic mobility assets. The one in the middle would bring an ascent vehicle for the people to come back. And then on the right is the human lander that would have I'm actually not sure which mission would carry this pressurized rover for the humans to land. So science objectives for a mission like this aren't defined yet. That's going to be worked on in the next several years. But one thing that is likely is I mentioned that subsurface access is an important thing for the future. So being able to drill deeper than we have today is one strong candidate for such a mission. And I'm hoping that we can do more work on the robotics so that that can play a greater role in improving the productivity of a human mission to Mars. And so I'm out of time. Thank you very much.
All right, we're at just about the exact time. Maybe we have time for one quick question if someone's really desperate.
I'm wondering, are there any natural sources of energy on Mars? And if so, what are they? Is
Well,
wind, thermal? No?
probably not thermal. Wind, it's a very thin atmosphere, so I'm not sure that we could do that. So, we use solar right now. That's not a lot. Yeah, solar, that's the main thing. So when you talk natural resources, there's also other stuff that people need. So water. So there's a lot of interest in the shallow water. If you get up to mid-latitude in the north, like 35 degrees north latitude, we think there's ice within a couple meters or, maybe a little bit deeper, but we think we can access shallow water. And that we can use for the people and also turn that into rocket fuel.
Hydraulic energy?
Yeah.
I see. Okay.
Get the hydrogen out to use it for propulsion for the return trip.
What is the pressure in atmosphere?
Well, it's about or the pressure. I always get pressure and density, about 1/100th of Earth. So numerically, the density is about 0.01 to 0.02 kilograms per cubic meter. So it's about 1/100th of an atmosphere.